Okay, continuing on, we're just looking at the intervals on either side of 2, and we noticed that the intervals on the right side of 2 got closer and closer to 4, and the intervals on the left side of 2 also got closer and closer to 4. So we're going to take a look at moving closer to the formal definition of an instantaneous velocity. So how small must we make the interval from 2 to a in order to get the exact value for the instantaneous velocity? Well, you can look at these intervals and say they're getting smaller and smaller and smaller. We really want to make them infinitely small. Okay, so if we find the limit of the average velocity, so let's take a look. What is average velocity for this scenario? It's a squared minus 4 over a minus 2. That's the change in y over the change in x. That's our average velocity, or the slope of our secant. Okay, but if we take the limit as a gets closer and closer to 2, meaning that interval gets smaller and smaller and smaller, then what we end up with is an instantaneous rate of change. At time t equals 2. Okay, thinking back to this graph, I'm just going to draw a little sketch here. Thinking back to this graph, the parabola centered at the origin. That's better. When t is greater than 0, what can you say about the average velocity values? Okay, what can you say about the slopes along this curve? They're all positive slopes. Okay, so we can say that velocity is positive. All right, when t is less than 0, if you look along this section of the graph, right, all of our slopes are negative. So here velocity is negative. Okay, so just kind of summarizing where we've been and what we've looked at, the average velocity is that slope of the secant line between 2 points. The average velocity is the ratio of the change in position, or the distance, to the change in time. So here we see an equation that says average velocity is v of t, change in position over change in time, change in s over change in t. And if we talk about between 2 points, a s of a and b s of b, then we're talking about s of b minus s of a, change in s, over b minus a. All right, so that's velocity, average velocity. Speed is the magnitude of velocity. All right, speed is the absolute value of velocity. Okay, speed is always positive or 0. Okay, instantaneous velocity We can think of it as the slope of the tangent line at a particular point or at a particular time. T equals a. All right, so the instantaneous velocity refers to the velocity at a particular point in time. But remember, this ratio is our average velocity. But once we take the limit and let the interval from B to A get smaller and smaller, so if B is moving closer to A, that interval is going to get closer and closer to 0. This is our instantaneous velocity. It's also known as the slope of our tangent line to the curve. All right, so just summarizing that, the limit, we could say as x approaches A of f of x minus f of A over x minus A. Again, average velocity, taking the limit, letting the interval get smaller and smaller, will result in instantaneous velocity. Okay, we're getting there. So now we're going to take a look at some examples using graphs and evaluating velocities. All right, so it says match the points labeled on the curve with the given slopes. So again, think about drawing a tangent line to the curve at the particular point. So if I look at E, for example, it looks like it's right at the top. My tangent line has a slope of 0. I'm going to think that at point E, that graph has a slope of 0. Now at A, it doesn't look like it's at 0, but it looks pretty small, okay, and positive. B is still positive, but it looks bigger than A. Where else do we have positive slopes? So A and B have positive slopes. D would also have a positive slope. So let's think about those 3 points because they're all positives. I have 3 positive values here. I'm going to put A with 1/2, and B with 1, and D with positive 2. All right, the other 2 points left on the curve have negative slopes. Again, I'm trying to draw a tangent line to the curve at that point. And it would appear that the slope at F is a lot steeper than the slope at C, even though I haven't drawn that one at F very well. All right, so we're going to say that C might have the slope of -1 and F has a slope of -3. All right, so again, these guys have negative slopes. Okay, for the same graph, arrange the following numbers in ascending order. Well, we already have some values for the slope of the graph at A, so I'm going to use those same values that we have up above, just to kind of give us something to go on here. The slope of the graph at E was 0. The slope of the graph at C was -1. So now let's think of the slope of the line EF and the slope of the line AB. All right, so the slope of the line EF, I should probably use the line tool. Maybe that would be better. Much better. And the slope of the line AB. All right, so this is definitely a negative slope. This is definitely a positive slope. All right, and I need to place it somewhere or give it a numerical value. So it looks like that this slope is less than -1, right? I'm just going to write that in there. Less than -1. I'm just estimating, right? And it looks like this slope, if the slope at A was 1/2, it looks like this slope is greater than the slope at A, so greater than 1/2. All right, so I think we have enough information to put this in order, right? And it's ascending order. So we'll start with the lowest, which would be the slope of EF, which is less than -1, then the slope of the graph at C, which we said was -1, then 0, 1/2, and greater than 1/2. All right. Okay, suppose the graph at the right is the velocity versus time for a butterfly in flight. When the velocity is positive, the butterfly is flying upward. When the velocity is negative, the butterfly is flying downward. Match the labeled points with the appropriate description. Some descriptions may fit more than once. So when is the butterfly flying the fastest? That means what is the largest velocity that we have? Okay. All right, and I believe that happens at E. The butterfly's velocity is increasing, but at a decreasing rate. Okay, so if the velocity is increasing, right, first of all, here the velocity is 0. And here the velocity is positive, and here the velocity is negative. Okay, so increasing, the velocity has to be going up. All right? But at a decreasing rate, so that means the slope has to be getting smaller, or be small. All right? So I would look at B because the velocity is increasing, or D because the velocity is increasing. But it looks like the velocity at D is increasing at an increasing rate, and the velocity at B is increasing but at a decreasing rate. So we're going to say B for this. All right, the butterfly is in a dive downward. All right. Well, when the butterfly's velocity is negative, it's flying downward. That can happen at 2 places. So we'll say it's either at C or at D. When is the butterfly flying the slowest? So we want a point that's closest to the x-axis because that would be the smallest velocity. And it looks like A is the point that's closest to the x-axis. All right, the butterfly's velocity is decreasing. Okay, so that means we want the curve to be going down. So that could happen at C or at F. We're looking for a negative slope. And the butterfly's speed is decreasing. So if we look at speed, if I could reflect this really nicely. Not exactly perfect, but you get the idea. All right, where is speed decreasing? Remember, speed is the absolute value of velocity, so I'm reflecting this negative portion of the curve above. All right, and then I'm looking for speed to be decreasing, so that's at D or at F. All right, where does the butterfly change direction? That means it's changing from going up to going down, or from down to going up. Well, here we're flying upward, and then at this point, the butterfly flies downward. So that would be a location that we could label G. Here the butterfly is flying down, but then switches and changes direction to fly up. So that could also be G.